Hello again. This is Math 2232 coming to you from the College of DuPage. And the title of this lecture is Hyperbolic Trigonometric Functions. As always, be attentive while watching this video. The catenary and its hyperbolic trigonometric cousins are very important in math history and in engineering applications even today. These are examples of catenaries, 3 examples. This one is the shape that a chain makes when hanging from 2 points. In the middle, we have freely hanging overhead power lines. They make a similar shape, and those are also catenaries. And on the right, the silk on a spider's web also is a catenary curve. So these are important curves, and that is one example of hyperbolic trigonometric functions. By way of continuing this introduction, a perfectly flexible chain in equilibrium suspended by its ends and subject to gravity has the shape of a curve called a catenary. The name was coined in 1690 by the Dutch physicist, mathematician, astronomer, and inventor Huygens in a letter to the prominent German polymath Leibniz. The catenary is similar to a parabola, which led the great Italian astronomer, physicist, and engineer Galileo Galilei, the first to study it, to mistakenly identify its shape as a parabola. The correct shape was obtained later and independently by Leibniz, Huygens, and the great Swiss mathematician Bernoulli. This is Johann Bernoulli. All 3 were responding to a challenge proposed by the Swiss mathematician Jacob Bernoulli, who was a big brother to Johann, to obtain the equation of this chain curve. We're going to follow a derivation similar to theirs. It's interesting that the Bernoullis were somewhat of a dysfunctional family. Johann Bernoulli was delighted that he had successfully solved the problem that his older brother had failed to solve. Later he wrote in a letter, "The efforts of my brother were without success. For my part, I was more fortunate, for I found the skill, I say it without boasting, why should I conceal the truth, to solve it in the full. It is true that it cost me study, robbed me of rest for an entire night. He stayed up late, pulling an all-nighter to get this done. It was a great achievement for those days and for the slight age and experience I had then. The next morning, filled with joy, I ran to my brother, who was struggling miserably with this problem, not getting anywhere, and always thinking like Galileo that it was a parabola. Stop, stop, I say to him. Don't torture yourself any more trying to prove the identity of the catenary with a parabola. It is entirely false." To find the equation of the catenary, the following assumptions are made. The chain or cable is suspended between 2 points and hangs under its own weight. The chain or cable is flexible and has a uniform linear weight density equal to W sub 0. So this is W sub 0, and we'll have that in our equations. Now the treatment here simplifies the algebra, so we're going to let the y-axis, because we get to choose our coordinate system, pass through the minimum of the curve. So this is the bottom of the hanging chain. The length of the segment from that minimum, from here, the minimum, to the point xy on the curve, on the chain, is denoted by S. That's the segment. It is S. It is a line segment, and the 3 forces acting on the segment are the tensions T0. This is a tension that is existing on the chain, and T1, or T rather. It's not T1, it's T comma, and T is the one pulling up, so that is the tension, and the weight is pulling it down. Now this is in equilibrium, so that means that the upward component of T, which is T sine theta, where that's the angle, has to balance out with the weight density times the length of the segment. And so T sine theta has to be the same as W sub 0 S. And since this is not moving back and forth this way, what we have is that the component going this way of t must balance with t0 found at the bottom. So these are two conditions that must be obeyed. Now, we know that the slope of the tangent line is the rise over the run, and if you look at this picture, you can say that the rise over the 1 is the derivative dy dx, and that's going to be the tangent. It is the rise over the run, the opposite over the adjacent, and so I have this tan theta. But now I can see what tan theta has to be, and to get tan theta I go up to these equations. If I take the bottom one and divide it by the top one, what happens is the t's will cancel. I will have tangent, and over here I will have w0 s of x divided by, and this is going to be t0. So now we have a differential equation, and what we're going to do is take another derivative of both sides. And so when I differentiate dy dx, I get the second derivative of y with respect to x. And w0 over t0 is a constant, but then I'm taking the derivative of this s, and s actually is, if you think about it in the limit, it is the arc length, but this is ds of x dx. And we've shown that ds dx, we called it like ds, but we said that ds is equal to the square root of, this is 1 plus dy dx whole squared under the square root times dx. That's one of our representations. Or you could think about it from a Pythagorean theorem kind of standpoint, but we know that this is true. So what we're going to do is we're going to substitute this in for ds dx, and we'll go to the next page to do that. So we have this. I've made the substitution for the arc length. And now, to address this in techniques that we studied in Calculus 1 at COD, if you need help with this, we'll explain it, but this is called separation of variables. It is one of our COD learning objectives from Calc 1. And it is studied in your book as well, so I'll make references to that later for anyone interested in that. But this is what we're going to try to solve, but it is convenient for us to introduce the following new variable. So we're going to say u is equal to dy dx. So that means that this is going to be du dx. There's our constant, and this is 1 plus u squared. And this equation can be integrated by separation of variables and solved. Now, when we do that separation of variables, we will get du over 1 plus u squared is equal to this other side, which is just dx. And so I will integrate both sides. And when I integrate this, I will get, and this is a trig substitution. You're substituting tangent of theta. But when you do that, what you'll get is that this definite integral is going to be, and this one is just going to be, you just get an x out of that. So what we get is the following equation. We get ln of the square root of 1 plus u squared plus u is equal to c, a constant of integration, and this is w0 over t0 times x. But since the y-axis passes through the minimum of the curve, we know that the slope of that curve at x equal to 0 is u at 0 because of our definition, n is equal to 0 because that's a horizontal slope. That's how we're simplifying the algebra. So if we take this, which is called equation 9, and substitute that into this equation down here, that enables us to figure out what the constant is. So we're going to take x to be 0, and we substitute it in, and we make note of the fact that, so this is going to be the natural logarithm of 1, which is 0, and x is 0, and so c is 0. So we know that the c is 0, and that tells us that what we have is then an equation down here, but we know that c is 0. Substituting c equal to 0 into equation 8, which is down here, and solving for u, we obtain an expression for u equal dy dx is this expression. 1/2, this is e to the w0 over t0 x, those are exponents, minus e to the minus w0 over t0 x. And that implies that y is equal to t0 over 2 w0, and this is e to the w0 over t0 x plus e to the minus w0 over t0 x. Now, we obtain this, and so this actually will be seen to be a catenary. Now, I am going to be assigning you, and I'm going to post this separately, but I want you to fill in the blanks here and actually do this step. And so that encourages you to read this, and actually it's some interesting algebra that happens here. So showing this part of the derivation to be true is going to be LSA 3 soon, and it will be separately posted, and I will give you some time to do this. Okay, with that introduction behind us now, let's start talking about the hyperbolic trigonometric functions. And just to show you some analogies, we know that the sine squared of theta plus the cosine squared theta is equal to 1. Often these are the trig functions are called circular functions, and we talk about them being defined on the unit circle. So if we were finding this area, what happens is we would be computing this integral. We know how to do this, and we would do we could do a trig substitution, or we could integrate it by parts. But anyway, we get this as an integral, and you see the inverse sign is involved. Now, what happens, and this is a formula we don't have yet, but we will have soon, is instead of having a circular function, if you have a hyperbola, then this area becomes what we will call the inverse hyperbolic sign, and that will be involved in that. So this is only one of many ways in which the hyperbolic functions are similar to trigonometric functions. So these are the definitions. This is the definition that we had for the catenary. So this is called the hyperbolic cosine of x is equal to e to the x plus e to the minus x over 2. The hyperbolic sine is e to the x minus e to the minus x over 2. The tangent of x, the hyperbolic tangent of x, is going to be the hyperbolic sine divided by the hyperbolic cosine. The hyperbolic cosecant is going to be the reciprocal of the hyperbolic sine, and the hyperbolic secant is going to be the reciprocal of the hyperbolic cosine, and the hyperbolic cotangent is going to be the reciprocal of the hyperbolic tangent. Now note that this is read, these words with the h there is read the hyperbolic sine of x, and this is read as the hyperbolic cosine of x, and so on. Now, math verbal slang has S-I-N-H pronounced cinch, and that rhymes with Grinch. And this is pronounced kosh, rhyming with gosh. These functions, of course, have graphs. Here's the graph of the hyperbolic sine or cinch, and what you see here is this is the difference between f of x equal e to the x over 2 and g of x equal e to the minus x over 2. You get this, the domain and range are minus infinity to infinity. The cosh or catenary is a sum of h of x equal e to the minus x over 2, and this is f of x equal e to the x over 2. You can see that you're summing these things, so the curve's going to look like that. It is the catenary, as we talked about. This is the hanging chain between supports on either end. The domain of this is minus infinity to infinity, but the range of this is going to be 1 to infinity. Now you can also look at the hyperbolic tangent. The domain is going to be minus infinity to infinity, and the range is going to be minus 1 to 1. And it makes you think of the arctangent, but it is different. And as you see, these are not identical at all to the circular trigonometric functions. Here's the graph of the secant. You do see that there are asymptotes that happen here at 0. This is the domain, and this is the range, and the domain and range are the same. That's a hyperbolic cosecant. This is a hyperbolic secant. Now this one does not have any asymptotes, whereas the secant really does. This is the domain, and that is the range. Now, although there's not vertical asymptotes as there was over here, there is a horizontal asymptote here, and then actually there's horizontal asymptotes up here with this one too. And this is the cotangent, and you see the cotangent looks very different than the hyperbolic tangent, and you have asymptotes, both horizontal and vertical asymptotes. These are the domains and ranges. Now also, many of the trigonometric identities have corresponding hyperbolic trigonometric identities. Here are some of them. You prove these by using the definitions of these trig functions. But the cosh squared minus the sin squared equals 1. Remember, it was the cosine squared of x plus the sine squared of x was equal to 1, but it was plus. And if you look at these, you're going to see that they are parallels. Some of them are the same, and some of them are different with respect to SIGNs. One must be careful using these identities. And you can take the derivative of the hyperbolic functions. Let's look at two examples down here. If I take the derivative of this hyperbolic sine of x, I'm taking the derivative of this. So the derivative of e to the x is e to the x, but the derivative of e to the minus x is minus e to the minus x, and a minus is a plus. So the derivative of the hyperbolic sine is the hyperbolic cosine. You might be saying, oh, so everything's going to work the same way. Not so much. What will happen here is that if you take the derivative of the hyperbolic cosine, you will get the hyperbolic sine, not minus the hyperbolic sine, but the hyperbolic sine. So you see the SIGNs are different here sometimes. So one must be careful with this. If we take the derivative of the hyperbolic tangent, that is the sinh over the cosh, it's going to be the denominator times the derivative of the numerator minus numerator times the derivative of the denominator, all by the denominator squared. But this cosh squared x minus sinh squared x is equal to 1, so that is 1 over this. So this is the hyperbolic secant squared of x. Again, things to memorize, and anytime you have a derivative formula, you have a corresponding integral formula. So these are more to commit to memory. Let's do some examples now. Let's differentiate some hyperbolic functions. And again, I'd encourage you to work these and then check the answer. But if we take the derivative of the sinh of x squared minus 3, that is going to be the cosh of x squared minus 3 times the derivative of what's inside by the chain rule. It is 2x. If we take the derivative of the natural logarithm of the cosh of x, it's going to be 1 over the cosh times the derivative of the cosh, which is the sinh, and so we will get the hyperbolic tangent of x. And if we take the derivative of x, sinh x minus cosh x, the first one is the product rule, so it's going to be the first times the derivative of the second plus the derivative of the first, which is 1, times the second. And then this is the minus sign. That minus sign is this one. And the derivative of the cosh is not the negative sinh, but the sinh positive. So when you simplify this, what will happen is this one will cancel with this one, and this is just x cosh x. Here's another example, finding relative extrema. So find the relative extrema of y equal f of x equal x minus 1 cosh x minus sinh x. You know what to do, and we'll go through the solution here. The graph of this is going to look like this, but we don't need the graph necessarily. So we begin by setting the first derivative of f equal to 0. So this is going to be the product rule. So it's the first times the derivative of the second plus the derivative of the first, which is 1, times the second, minus, and this is the derivative of the sinh, is equal to 0. Now this will cancel with this, so I have this. Now there are two factors here. So the two critical values are going to be, if I set x minus 1 equals 0, I get x equal 1, and the sinh is 0 when x is equal to 0. Now we're going to use the second derivative test. We can verify that this point, which is 0 minus 1 yields the maximum, and the other point yields a relative minimum. Now this is the point 1 minus sinh of 1. Now that is e to the 1/2 minus, or excuse me, it is, you use the definition. So to evaluate what this is, you would plug this into a calculator, but you would use the e definition, and that's the min, and you see what happens over here. And again, minus sinh 1 is a number. And so that's what we have here. And you can always use the exponential function to do that as well. And so you could have written it this way, and you could say, oh, this is the cosh and this is the sinh, and you could plug it in that way. And in fact, most graphing utilities don't have hyperbolic functions. We've already talked about this a great deal, but when a uniform flexible cable, such as a telephone wire, is suspended from 2 points, it takes the shape of a catenary. And so here's an example. You could practice this, but here we have that this is from minus b to b, and we have A is the intersection right there. That's the minimum height that happens. And so the equation for the catenary is y equals a cosh x over a. So the distance between the two towers is 2b. Find the slope of the catenary at the point where the cable meets the right-hand tower. So you want to find the slope right here of the catenary. And again, the catenary continues going up like that, so this isn't a cusp. So you want to find the slope there. So we take the derivative, and so y prime is going to be, the a just sits there. The derivative of the cosh is the sinh, x over a, but then we use the chain rule, that is 1 over a, so we get this as sinh x over a. Now at that point, what we have is, oh, it was the right-hand one, it's this one. So it's b, so we're substituting x to be b, but then we get cosh b over a, and so the slope is given by m is equal to the sinh of b over a, because here was the derivative, so that is the slope. You can also integrate hyperbolic trig functions. Here you have sinh squared of 2x, cosh 2x dx. Well, we do a u substitution. We let u equal sinh of 2x, and we use the chain rule. We get that this is 1/2, and you raise this exponent by 1 and divide by the new exponent plus c. So it is sinh cube 2x over 6 plus c. There are also inverse hyperbolic trigonometric functions. Unlike trigonometric functions, hyperbolic functions are not periodic. You don't have any 2 pi kind of things. In fact, looking back, you can see that 4 of the 6 are actually 1-to-1. And so, and the other 2 are 1-to-1 if the domains are restricted. And so what we end up with is we have actually a rich set of hyperbolic inverse functions, and this is a theorem, and this would be something that I think would be really a great exercise for you to prove. But we have that the inverse hyperbolic sign is the natural logarithm of x plus the square root of x squared plus 1. And the proofs of these theorems, we're using the fact that the exponential function and the natural logarithm functions are inverses of each other. And in fact, down here it says the proof of this is straightforward. I don't know how straightforward it really is. I'm going to suggest that you give this a try as an exercise and see how straightforward it really is. but they're going to say that this function and this function would have to be inverses. And so that would be, what you would have to do to verify this. And so these are examples of the inverse functions with their domains. And they have graphs. So this is the graph of the inverse hyperbolic sine, inverse hyperbolic cosine, inverse hyperbolic tangent, and so on. Now, the inverse hyperbolic secant, which is this curve right here, can be used to define a curve called a tractrix or pursuit curve. And this actually has a lot of applications in military matters and things like that. And we'll look at an example of that momentarily. In fact, right away. So a person is holding a rope that's tied to a boat. So the boat's out here, and it's as shown in the picture. A person walks along the dock, and the boat travels along a tractrix. So you see the person's pulling the rope, but what happens is the boat comes in like that. So it actually follows a tractrix. And this is the equation that we have for that. Y is equal to a hyperbolic inverse, the inverse of the hyperbolic secant, x over a, minus the square root of a squared minus x squared, where a is the length of the rope. So if a is equal to 20, find the distance the person must walk to bring the boat to position 5 feet from the deck. Okay, so they have to walk. Notice the distance the person walked is given by, you add y to this, okay? And so you get this, and so this, when you simplify all of this, and you see this thing cancels with that thing, and so we get 20 hyperbolic secant inverse of x over 20. So when x is 5, you plug in 5 into this, and you do the calculation. Now we have an expression for this inverse hyperbolic secant, and it was this natural logarithm. So we're actually plugging in the numbers into there, and 5 over 20 is the same thing as 1/4. And so this is the exact answer, and this is what you get if you plug it into a calculator. Now we can also take the derivatives and integrate. You notice those were pretty smooth curves. So we can take the derivatives, and they were continuous curves for the most part. So we can differentiate and integrate inverse hyperbolic functions. And so we're going to take those derivatives, and we get this as a set of new derivatives. You'll notice that there's a chain rule. And every time you have a derivative formula, you have an integral formula. Now these are integrals that some of these are integrals that you haven't done before, and this is giving the expression for that. So these are some integrals that are new integrals for you, and you can use these to solve problems that you couldn't solve before. So again, a lot to cover and a lot to commit to memory here. For the tractrix that we had in the previous example, show the boat is always pointing towards the person. Well, that means we're going to take the derivative. And so we're going to take the derivative of these functions. Using the formulas that we have, we will get this. And when we simplify, we will get this expression. But from the figure that we looked at before, you can see the slope of the line segment connecting the point 0, y1 with the point xy is the same thing, except they're in different, it is exactly the same thing. So you're always pointing toward the person. It is because of this property that this is called a pursuit curve. If you're shooting a rocket to shoot down a plane, you would want it to pursue the plane. This is an example using the formulas that we have for the inverse hyperbolic functions to do integrals. So for example, this one, integral, you let a be 2 and u be 3x, and it's this bottom one that we can use. So we make that substitution, and we simplify, and we get this as our answer. You can also do another one. If you were confronted with this problem, you'd let a equal the square root of 5 and u equal 2x, and do the substitution. And here we would be using the top formula from the theorem that we had. And we go through, make the substitution, do the algebra, and this is the answer that we would get, algebra and arithmetic. And this is the answer we would get at the end of this problem. Now on your calculators, what you can do is you can program in with the exponentials here, and that's what you might want to do. Most calculators, even a very robust calculator like a TI-84 Silver Edition, doesn't have any buttons for the hyperbolic things, so either you type the things in to do it, or you create functions with your function keys. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.